We've been looking at the mean value theorem. Let's take a look at something interesting that happens when we add in another hypothesis, which is that f of a is equal to f of b. So we still have that our functions are continuous from a to b and differentiable from a to b. But now we're adding in that f of a is equal to f of b. This means that f of b minus f of a is equal to 0. So we have 0 over b minus a. And since b and a are not equal to each other, that means that their difference won't be 0. So we just have a 0, as opposed to like a 0 over 0. So that means that f prime of c is equal to 0. It also means that the slope of the secant line between a and b is 0. So we have a horizontal secant, which means we're also looking for horizontal tangents. For our first function, this happens twice. So the slope of the tangent at c is equal to 0 twice for our first function, and then the slope of the tangent is equal to 0 3 times for our other function. What you might notice from looking at the graph, or you might remember from looking at minimums and maximums, is that each of these points occurs at a local minimum or local maximum. Because when the slope of the tangent line, or when the derivative at a point is equal to 0, we have a local minimum or maximum usually. Or at the very least, we know that we found a critical number. Because this case is so interesting, it actually gets its own name. We call this Rolle's theorem. So we still have that f is continuous over the closed interval from a to b, and that f is differentiable on the open interval from a to b. But we're adding this third condition, that f of a is equal to f of b. This special case of mean value theorem has a slightly different conclusion, which is that if all 3 of these criteria are met, then there is a number c in the open interval from a to b such that f prime of c is equal to 0. Let's take a look at 2 examples. First, we want to verify that the function f of x is equal to x cubed minus x squared minus 6x plus 2 satisfies the 3 hypotheses of Rolle's theorem on the interval from 0 to 3. Then we want to find all numbers c that satisfy the conclusion of Rolle's theorem. So first, let's verify that f of x satisfies the 3 hypotheses. So first, we need to verify that f of x is continuous on the closed interval from 0 to 3. Then we need to verify that f of x is differentiable on the open interval from 0 to 3. So those are the 2 conditions from mean value theorem. And then we're adding on this extra condition that makes it so that we have Rolle's theorem, which is that f of 0 has to be equal to f of 3. F of x is continuous and differentiable over our interval because f of x is a polynomial. Which we know are continuous and differentiable over their domains. Verifying the third hypothesis, that f of 3 is equal to f of 0, will take a little more work. We actually need to evaluate our function for each of these inputs. So we have to find f of 0, which would be equal to 0 minus 0 minus 0 plus 2. So f of 0 is equal to 2. we also have to find f of 3, which would be equal to 27 minus 9 minus 18 plus 2, which is also equal to 2. Since f of 3 and f of 0 are both equal to 2, we know that f of 0 is equal to f of 3. Since this function satisfies the three hypotheses of Rolle's theorem over this interval, we can conclude, so there must exist a number c on the open interval from 0 to 3. I'm not sure why I made that parenthesis so big, such that f prime of c is equal to 0. Now that we've verified that our function meets the hypotheses and we've stated our conclusion, we want to actually find all the numbers c that satisfy this conclusion. We'll start by taking the derivative of our function. So f prime of x is equal to 3x squared minus 2x minus 6. And then we're interested in where this derivative is equal to 0. Since this is a quadratic expression and it's equal to 0, we can jump straight to the quadratic formula. So we have x is equal to 2 plus or minus the square root of 4 minus 4 times 3 times negative 6 all over 2 times 3. So this is equal to 2 plus or minus the square root of 4 minus plus 72 over 6, which is equal to 2 plus or minus the square root of 76 over 6. We need to check to make sure that these numbers are actually in our interval. So we need to check to make sure that these are actually on that interval from 0 to 3. First thing that's the easiest to check is whether or not one of these will end up with a negative number. Since we have that 0, we know that both of these numbers have to be greater than 0. So we'll take a look at that 2 and compare it to the square root of 76. 2 is equal to the square root of 4, which is less than the square root of 76. So that means that 2 minus the square root of 76 is going to be less than 0, and 2 plus the square root of 76 is going to be greater than 0. This 2 minus the square root of 76 is less than 0, so it's not on our interval. Since we have at least one c that satisfies our condition, that means that this 2 plus the square root of 76 has to be the numerator for our interval. So c is equal to 2 plus the square root of 76 over 6, which we could simplify to 2 plus the square root, so 2 plus 2 root 19 over 6, or simplify further to 1 plus the square root of 19 over 3. Let's take a look at one more example, this time with a trig function. So we want to verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval, then find all numbers c that satisfy the conclusion of Rolle's theorem. Our function this time is f of x is equal to sine of the quantity x over 2 on the interval from pi over 2 to 3 pi over 2. So first let's verify that this function satisfies the three hypotheses. So first we have to make sure that f of x is continuous on the interval pi over 2 to 3 pi over 2. Not sure why I wrote 3. We also have to verify that f of x is differentiable on the open interval from pi over 2 to 3 pi over 2. And finally, we must verify that f of pi over 2 is equal to f of 3 pi over 2. Sine of x is continuous and differentiable over its domain, so the first two conditions are met. So once again, sine of x is continuous and differentiable for all real numbers. To verify that f of pi over 2 is equal to f of 3 pi over 2, we'll have to do a little more work. We'll actually have to evaluate our function at these values. So we need to find f of pi over 2, which will be equal to the sine of pi over 2 all over 2, which is equal to the sine of pi over 4, which is equal to root 2 over 2. We also have to find f of 3 pi over 2, which would be equal to the sine of pi over 2, 3 pi over 2, 3 pi over 2, all over 2. So that's the sine of 3 pi over 4, which is also equal to the square root of 2 over 2. Since f of pi over 2 and f of 3 pi over 2 are both equal to root 2 over 2, that means that f of pi over 2 is equal to f of 3 pi over 2. So we've verified the three hypotheses of Rolle's theorem, and we can state our conclusion. So there must exist a number c on the open interval from pi over 2 to 3 pi over 2, such that f prime of c is equal to 0. Now we have to find the values of c that satisfy this conclusion. To do this, we'll start by finding the derivative of f of x. F prime of x is equal to the derivative of sine of the quantity x over 2, which will require us to use chain rule. The derivative of sine is cosine. So we have cosine of x over 2 times the derivative of x over 2, which is 1/2. So f prime of x is equal to 1/2 cosine of x over 2. And we're interested in where this is equal to 0. So we'll start solving for x. First, I'll multiply both sides by 2, so I'm left with the cosine of x over 2 is equal to 0. There's a couple different ways to do this. One way is to take the inverse cosine of both sides, so we're left with x over 2 is equal to the arc cosine of 0. So that means we're looking at where the cosine of something is equal to 0. Sometimes I like to think of this as the cosine of m is equal to 0. The cosine of m is equal to 0 when m is equal to pi over 2 or 3 pi over 2. So that means that I have x over 2 is equal to pi over 2 or 3 pi over 2. So x is equal to pi over 2 times 2, which is just pi, or 3 pi over 2 times 2, which is 3 pi. Now I need to check whether or not these are on our interval. So are they between pi over 2 and 3 pi over 2? Pi is on this interval, but 3 pi is not on our interval. Since we had 2 options, and one of them isn't there, and we know that at least one solution exists, that means that C is equal to pi.